Okay, so we have cleared away what is composite, advantage and disadvantage, clear away types of matrix. Now we talk about the types of resin. So I believe the McDonald can play composite is very familiar to you right now, and therefore we talk about the reinforcement. We can use particle, we can use fiber, or we can just structural reinforcement. So what all these things we'll be talking about in this video. Before going into the details, I'll just give you a quick review of what are all this. Alright, so once you understand everything, the rest is just trying to add on to the meaning. Alright, to make things, to sink things more deeper. So there is a large particle and there is a nanoscale dispersion. So what are all this for particle reinforcement? For particle reinforcement for a large particle, you can also use the chocolate Hershey's cookie. Alright, so these are all the large particles, your chocolate, Hershey's chocolate, and these are all your materials to make your cookies. Okay, and within I think there is some coconut, whatever thing that is inside, but at least these are the large particles. In terms of the nanoscale, alright, the nanoscales is talking about maybe you, although it's not very true, but sugar, alright, your egg or whatever is mixed inside all this to make your crust, alright, your material over here, this crust. Alright, so you put in a lot of sugars, everything, whatever materials, your flour, whatever. So these are all nanoscales material. Alright, so you are just mixing in. So these are all the particles, and whatever thing that makes up the crust is your nano reinforcement. Now we have done this large particle and the nanoscale dispersion. Now is continuous long aligned and discontinuous short. Alright, so this means that the reinforcement fiber, alright, if you have a matrix, for example, let's look at the top view. Alright, you have a long alignment. These are all long alignment fibers. Okay, so this is continuous long aligned. If it's a discontinuous short, alright, this means that you may have something like this. Alright, you may have something like this. These are all aligned continuous short. So as you can see, it's aligned, but under the discontinuous short, these are all aligned. So they are aligned in this direction, alright, all straight. If it's random orientation, this means that it's randomly aligned. Things like that. Okay? Therefore we have done this, and this. Now the next one is laminate and sandwich plate. Laminate by definitions, if you got do laminations, you have your set. Alright? You join a singing competition and you have a set. And then you say that you don't want to crush it because it's a paper. So you go to the lamination shop and then you laminate using a plastic. And then you cap. And it becomes a laminated thing. So it's just laminations. So you can laminate multiple layers, things like that. Alright. As for the sandwich, it's just your burger, and then this is maybe your ham, your tomato, your ham, and then your lettuce, whatever, and then your bread. So this is your sandwich system. Therefore, under structure is laminate and sandwich plate. So you either laminate your structure or you sandwich your structure. For fiber reinforce is put inside, so it's either continuous or discontinuous. And then for particle reinforcement is you mix like Milo like that. Mix. Therefore, to go into details, let's go into the particle reinforcement first. Alright, the particle reinforce either a large particle or either the nanoscale dispersion, meaning very small particles that you cannot see with your eyes. So in this case, this particle reinforcement, as we say, is, I believe these two pictures are talking about the nanoscale dispersion, although this in terms of micro scale or micrometer. But anyway, so the tungsten WC is for brittle hard. So the particles is for brittle and hard, while the other the cobalt material is for ductile and tough. So they mix both of them together, alright, in order to mix them up. And then as for over here, this is for the rubber or your tire. As you can see, it's a Goodyear tire and rubber company, I don't know what. Alright, like Michelin. But anyway, so these are all your carbon black stiff. Alright, while these are your rubber polymer, things like that. You may want to just take note of it. Okay, so this is something like your particle reinforcement. I don't think you need to memorize. You can see the key thing to take away is that you mix different properties together. Alright, you mix different properties all together at once. Alright, into a bowl. Alright, while instead of the other methods, they are all individually by themselves. Alright, in this case for the particle reinforced is you mix everything together at once. Okay, and for fiber reinforced, which is the next one, this one, okay, this is the group coming up next, is the continuous, align, and so the align you can own self read. I think I've explained it quite significantly well, and continuous and align, I think you all know already, is just one line, one line, one line, one line, like that. For align, you need to know is that the properties of the aligned fiber reinforced composite materials are highly anisotropic, meaning physical property which has different value in different directions. Okay, so this is just the meaning of that. And then you need to also know that the interfacial bond, meaning the face of each of the bonds, meaning this is, let's say this is the fiber, this is the matrix, so the interfacial bond which is in between them, and the presence of voids. So in between them there may be some air voids. So in terms of the properties, the strength, everything, you also need to determine their interfacial bond and the presence of their voids, things like that you may want to understand. Okay, so these are the things that will affect the strength of the aligned material also. Okay, and it's more catered for the tensile ability lah, or tensile strength when you pull. Alright, and as for the continuous one, it's most effective strengthening for fiber composites. So I will believe continuous and aligned is better than the aligned method. Okay, I will assume. Okay, maybe wrong. For this continuous and aligned, alright, is this one. Okay, why we use this is because it's faster and cheaper, faster and easier to fabricate into whatever shape that you want. Okay, however, they are composite modulus, meaning the tensile strengths, alright, can approach 50 to 90% of their continuous and aligned counterparts. So if you were to compare this continuous and the continuous, which is this one, alright, the discontinuous, the strength is much lousier, but it's easier to fabricate. But if talking about shapes, different shapes, then I think this one will also be very, very good in a certain sense. Okay, for random one is that your material will be isotropic, meaning in all directions the force are the force that you can tank is the same, or I mean isotropic lah, and cheaper also lah. So this is the random aligned one. And the next one is woven, which we didn't actually say just now, but you just need to know that there is a woven fabric fiber, where it is also strong in all directions. So the woven one is like a random one. Okay, while the random is like this, the woven one is like this. But why do we choose this than this? Is because they are all connecting together very strongly, knitted, somewhat like knitted. Compared to this one is very dispersed. So anytime you pull, it just deform. For this case, they are all knitted together, so it's very, very strongly closely related. Okay, there are more other stuff for the fiber reinforcement. Okay, so now we talk about just some cross-sectional visualization. So the cross-section means that your fibers, or if you were to go into 3D, okay, give me a while. So this is your fibers, it's going in 3D, you see. So this is your fibers, so this one is also your fibers. So different shapes, different fibers. So you can also design the fibers, the shapes of the fibers, things like that. So they are just comparing to you the different the cross section, the size of the cross section. So there is 3 types. The first type is the whiskers. Remember, the whiskers is just the smallest one, as you can see, very small. Alright, and the next one is the fibers, which are all this, okay, and the wires, which is very big, this one. Okay, so I will believe this one, maybe not. You give me a while. You know that there is whiskers, there is fibers, and there is wires. Alright, because as you can see, the whiskers can be very small, while over here the wires, or your fibers, I think, is, as you can see, your whiskers over here is bigger than your wires and fibers also. So these are all, you see, wires, so it's wires, and then your carbon fibers. So your fibers and your wires is somewhat about the same size, but approximately this thing. Alright, so wires have large diameters, small diameters. I think you can also go and read yourself lah. Okay. As for the fibers, it can be polycrystalline or amorphous. So polycrystalline is something like this, half crystalline, half amorphous. Okay. while the amorphous is just anyhow random whack only. Alright, crystalline is very nicely aligned. So the fibers is like this lah. Okay, and then wires made of steels, and whiskers are expensive. Alright, so it's tough to actually put inside the matrix, and therefore requires a certain skills and machines to design. So that's why it's expensive. Alright, because it's so small, alright, it is flawless. Okay, so therefore it's very very good to design for high strength or whatever that you want. And this page is just to show what type of fibers do you use, or ceramic or glass, alright, and what are the examples that you can see, or different materials, things like that, alright, that you may want to understand. I don't think you may want to memorize that, but just take note of it lah. Okay. So over here, as the name suggests, is that you grow your fibers. So you have your catalyst nanoparticles. So you place it over here, it will grow in the end, and then it becomes this. So it become bigger and bigger. So this is your roller. So you roll, and each of the piece you will have your particle, and then once you roll to a certain stage, so this is the light. So you shine the light, and then this thing will grow, and then after that, once it grow finish already, then it will go into the next one, and then whatever thing that is over here will come into the light again. So this light will actually shine on it, and then it will grow. So you keep on growing and growing, so you'll grow a series of composites out. These are the other examples that you can see, but I just want to show you is that over here, this portion over here, as you can see, I don't know whether you can see this portion, alright, is that it's very stiff and very strong. As you can see, the fibers are all crumpled all together in this side, while over here there is lesser fibers, and therefore it's less stiff and less strong. So if they ask you to draw something like very stiff and very strong fibers, then you can draw like this. Alright, if you have a very less stiff and less strong, then you're just something like that. That's all, less fibers. So these are the things that you want to suggest. Okay, and these continuous fibers in terms of a random, alright, so you randomly align. As you can see, they are all randomly aligned. Okay, they are all random. So you randomly align in 2 dimensions, meaning the x-axis and the y-axis, like this. Okay, so at this stage it's talking about fabrics line in plane. Alright, so different planes, alright, in terms, then you have a different fibers orientations, random orientation, so to speak. For example, if you have a 2D, alright, you have some fibers, okay, some fibers, alright. If it's 2D, if it's 3D, then you can talk about another plate, alright. If it's somewhat random in 3D, alright, random in 2D. Okay, random in 2D, this means that you random at this plane, alright, at the bottom, exactly, you also have this fibers also. Okay, exactly at the same spot, you also have the fibers, and we call this the fibers that line in plane. Alright, so all the fibers line in plane on this, and this in terms of a 2D design. So if you have a 3D design, instead of having the same line, same orientation all along the piece, alright, you may have different orientation already. So maybe you'll have something like this. So you totally randomly anyhow whack. Okay, so this is in terms of 3D. Alright, Z direction, random 3D. If it's random 2D, at least it's just 2D. Alright, so all throughout the whole height. So this is the height. Alright, so throughout the whole height, they're all random in terms of 2D only. Okay, so this is the key key component that I just want to say. Therefore, if it's 2D, then this means that it's discontinuous aligned. If it's discontinuous random 3D, then it's the one that I say is 3D and randomly. If it's discontinuous aligned, then this means that it's aligned in 2D, I think. Sorry, it's not. Discontinuous aligned is the one that I told you early ago. discontinuous align, something like this. They're aligned, that's all. Okay, sorry. And then so it can be random 3D, can be random 2D, as you can see. So if it's 2D, the K will be different. So this is your constant, your fiber efficiency factor. Okay, so as you can see, if it's 2D, the efficiency factor is about 0.375. I think, yeah. So I calculated. So 38 is about 0.375. If a random 3D, your efficiency is 0.2. So you want to have a 2D random so that you have a higher efficiency factor K. And next up is the formula that is shown here. And the K, we say that the efficiency factor is for the fiber efficiency factor in terms of the random 3D or 2D. Okay. As for the overall equation, is that you are calculating for your Young modulus of your composite. Alright, so in order to find your composite for Young modulus, you need to have your Young modulus for your matrix material, alright, and your volume ratio, and V is your volume ratio, E is your Young modulus. So this is for your matrix, denoted by M, and F is denoted by the fibers. And if you find this familiar, this is actually from your materials. Alright, these are the formulas. I think you find it pretty familiar. Okay, and these are all the calculations you have to find. Some of the second moment of area, I think I forget already, but these calculations that you have done in the past. Okay, and the rules of mixture, you can search for all this lah. Okay, and yeah lor, so these are the things that you may want to check it out if needed. If not needed, then you can just heck care this. Okay, and after talking about so much on fiber reinforcement, we have already said particle reinforce, alright, the cookie, alright, the chocolate chip, everything. So we have, after that, then we talk about the fiber reinforcement, and therefore now we talk about the structural. Where the structural, we talk about the laminate or laminations. Lamination, you stack. Alright, normally previously we say lamination is you take the paper and then two plastics and then you put together. So in this case, each of the sheet, as you can see, if I to zoom in, okay, if I to zoom in over here, as you can see, each of the sheet is laminated in different directions. As you can see, they're orientated in different directions. So you just stack them in different directions, 90 degrees or whatever, and there will be calculations in the Excel sheet, which I show you in some other videos. Alright, yeah. So if you were to join this website, you can actually download, then you can calculate for your everything that you want. Okay, so I think this website is pretty good. Everything calculation, all the Excel what you want to find can be found here. So I think not bad. But anyway, this is the thing for the structure. So you can actually calculate for the sequence. So once you stack them together already, you will know in every directions what is its tensile strength and things like that. Okay, and this is for the lamination part. For the sandwich, the sandwich panel part, alright, you just need to know there is a face sheet and there is an adhesive layer. Adhesive layer is that there will be a layer where you apply the adhesive, and then after that they will stick onto this, and then bottom also adhesive, then they will stick onto the honeycomb, or the honeycomb structure, and then together they will become like this. That's all it is lah. So this ends the whole lesson 1. Okay, and just to say is that this thing you can remember, alright, continuous, short, or whatever, random orientation, 2D or 3D, or there will be calculation also. Alright, and you also need to know that for the fiber reinforcement, you are talking about the size of the fiber, whether is it a whisker, fiber, or wire, what is the size and things like that, which you can easily assess from this cross-sectional thing. Although it's not very well defined in this slides, because the fiber, they say whiskers is the very small one, and then the whiskers is larger than the fiber. I don't know what the hell is going on, but anyway, you just need to know what they want, then okay already. Okay, and then that's all it is, and see you soon.